All right, welcome to this explainer where today we're going to get our hands dirty. Well, digitally speaking, anyway. We are building an AI that knows its dirt, literally. It's going to learn to tell different soils apart just from a picture. So here's the big question, right? Can a computer really learn to identify different types of soil just from a picture? Can it tell the difference between, say, peat and cinder soil? It kind of sounds like sci-fi, but believe it or not, the answer is a huge, resounding yes. And you know what? It's not only possible, but over the next 5 minutes, we're going to show you exactly how it's done. And we're going to use this really powerful tool called PyTorch to pull it all off. So, you ready? Let's dive in. Okay, so here's our challenge. We're building what I'm calling the AI soil sorter, and the mission is super specific. Teach a machine to classify 5 distinct soil types just by looking at images. We're talking black soil, cinder, laterite, peat, and yellow soil. Now, to build something like this, you obviously need the right tools. And for us, the essential tool in our toolbox is PyTorch. The best way to think about it is like this. It's a deep learning framework, basically a super-powered kit for building and training these artificial brains, or what we call neural networks. It's going to handle all the heavy lifting for us. All right, so every AI model needs data, right? And just like in cooking, preparation is everything. Our ingredients are thousands and thousands of images of soil. And just like a chef, we have to prep these ingredients, these images, before we can feed them to our AI. And this prep work follows a pretty standard pipeline. First, we just load up all the images. Simple enough. Then we resize them so they're all the same size, and we do something called augmentation, which is just a fancy word for flipping them, rotating them, kind of mixing them up to give the model more to learn from. Step 3, we convert them into tensors, which you can just think of that as the language computers speak, a big grid of numbers. And finally, we normalize everything, which just helps the model train faster and better.
We trained a soil type classifier using a pre-trained ResNet 18 model in PyTorch. First, images were loaded from folders: black, cinder, laterite, peat, yellow soil, resized, and augmented. The model learned soil features through training, and we saved it as soilcalculator.pth. When we test a new image, the model processes it, applies softmax to get probabilities, and predicts the most likely soil type. In the output, it correctly predicted cinder soil with about 76% confidence, meaning the model is fairly sure but not 100% certain.
And here's where you really see the magic of a tool like PyTorch. All those steps we just talked about, loading, resizing, augmenting, the whole deal, it all gets bundled into this one super clean line of code transforms.compose. It's like our perfect recipe for data prep, and it runs exactly the same way every single time. Okay, our ingredients are prepped and ready to go. So now we need the blueprint for our AI's brain. And here's a pro tip. Why would you ever build from scratch when you can, stand on the shoulders of giants? We're going to borrow a brain that's already incredibly smart. So check this out. Building a neural network from scratch, man, that's a massive undertaking. It can take months of training, you need huge data sets, tons of computing power. It's a whole thing. But there's a much smarter way to do it called transfer learning. We basically take a model that's already been trained and just repurpose it. It saves time, it saves data, it saves money. It's working smarter, not harder. And believe it or not, this is the line of code that makes it happen. That's it. We're calling out a famous pre-trained model called ResNet 18. And that little part there, pre-trained equals true, that's the secret sauce. Without one command, we've basically just downloaded an AI brain that's already an expert at seeing general shapes and textures and patterns. But here's how we customize it. We don't want to mess with all that knowledge it already has, right? So we freeze the existing layers to keep all its general wisdom about shapes and stuff. Then we just snip off the very last layer, the part that makes the final decision, and we swap it out with a brand new one that's built for our specific task, classifying those 5 types of soil. It's like a brain transplant, but just for one tiny part. So now we move on to the assembly line. This is where the real learning happens. We've got our prepped data, we've got our customized AI brain. Now it's time to teach it. The model is just going to look at our soil images over and over and over again, refining its knowledge with each pass. And we measure this process in something called epochs. It sounds technical, but it's super simple. One epoch is just one complete pass through our entire training dataset. And the idea is, with every single epoch, the model gets just a little bit smarter. Okay, so after the very first epoch, the models first look at all the data. Its accuracy is at 58%. Now, that's way better than just guessing, which would be like 20%, but yeah, we've still got a ways to go. But just watch this. We fast forward just a little bit to epoch number 8, and boom, the accuracy has shot up to 85%. You can literally see it learning. The repetition is working, it's starting to pick up on the unique patterns of each soil type. And by the time we finish our training run, after 15 full passes through the data, we hit an incredible 94% accuracy. Our AI soil sorter is now a legitimate expert. The assembly line worked perfectly. But a high accuracy score is great, but it doesn't tell you the whole story. It's time for some quality control. We need to check the final product and see how well it actually performs on a more granular level. So this is a simplified look at what's called a classification report. It gives us two really important numbers. Precision asks, when the model says it's cinder soil, how often is it actually right? And recall asks, of all the real cinder soil pictures out there, how many did our model successfully find? And as you can see, with numbers in the 90s for both, it's doing an amazing job. It's not just accurate, it's also not missing much. Okay, metrics are great, but here's the moment of truth. Let's give it a brand new image, one it has never, ever seen before. We're feeding it the path to a cinder soil picture, and let's see what it says. And there it is. Predicted soil type, cinder soil. It nailed it. Perfect. Test passed. But it gets even cooler. The model doesn't just give us an answer. It tells us how confident it is. And in this case, it's 75.8% sure that it's right. For a real-world test on a new image, that is a fantastic result. So let's just pause for a second. We went from a bunch of code and a folder of pictures to a genuinely intelligent application in just a few minutes. So, what does this all mean? Why does this matter? The big picture here, the main takeaway, is the sheer power of frameworks like PyTorch. They automate all the ridiculously complex math. They give us these incredible pre-trained blueprints like ResNet 18 to build on. They make handling all the data a breeze. And what that means is it enables pretty much anyone to build powerful AI applications and to do it fast. And that brings us right to our final question for you. We just taught a computer to see soil. I mean, think about that. If we can do that this easily, what comes next? If you could teach an AI to see and solve any real-world problem, what would you choose?